Let's learn about IPv4 packet structure. That is IPv4 packet header format or structure with the help of Wireshark. Wireshark is a powerful packet analyzer and that can be used to troubleshoot. It is also best used in learning protocols. What is IPv4? IPv4 is a Internet Protocol version 4. It is widely used even today, even we're running out of addresses. But it is which layer network internet layer protocol or a network layer protocol in OSI model. And in this layer, routing happens. Routing means, and in this layer, we have the PDU is called a packet or datagram, and routing happens in this layer. And routers take care of making decision about whether to which network that packet should be forwarded based on the routing there. And so the best way to, what is the packet structure? And we have learned there are different layers. OSI model, in the OSI model, how many layers we have? Yes, 7 layers. And in TCP/IP model, we have four layers, or sometimes also referred as 5 layers, with the first layer counting as 2 data link and physical layer, physical and data link layers. And if we have learned about encapsulation also, where every top layer is encapsulated, takes the service from the underlying layer, and the data is encapsulated into the underlying layer, and the data is actually data is encapsulated into underlying layers payload or a body. So here, what is a and if you take if you take any protocol, mostly that protocol would be having a header and body. If you take a IPv4 packet, and that packet also contains header and body. What is header? Header carries metadata, information about what is information about what data is actually it is carrying, and checksum, and the source and destination addresses, such a thing, mostly about the data is stored or presented in the header. And we have here, as you can see, this is a typical structure of the IPv4 packet, where you have the header and then body. So what is the format of header? And there is no such a format, there is no defined format for the data. Data can be anything. And here, in fact, the data is actually the data that is coming from the upper layer, that is a transport layer, and that whole transport layer segment is encapsulated into this IPv4 datagrams payload or a data. And what you have here is the standard structure of the header, and you have header is of how many? This header is of at least 20 bytes and maximum 40 bytes, because there is a fixed length minimum of 20 bytes header, and there is optional data or there is optional options or padding, which is of up to 40 bytes. So if a header is of 20 bytes as well as including 40 bytes, and header will be of a total 140 plus 20, 60 bytes. Otherwise, it will be, if there are no options or padding, it will be 20 bytes. And header, it is counted in a watts. And in a binary, if you recall, so 8 bits are called as a 1 byte, and 2 bytes are called sometimes a 2 byte word, or 4 bytes are called as a 4 byte word. So it is structured in such a way, so each line is having 4 byte word. So you can see here 0 to 8, it is 1 byte, and TOS, this is 1 byte, and 16 to 31, which are 16 bits, which means 2 bytes, and total 4 bytes we have. And the first line is about the packet, which contains the version and header length, IHL and this is also sometimes called as a H length, header length, and type of service, TOS transfer, and total length we have here, which describes the length of the total packet, which includes both the header and the data. It includes the whole length of the packet, it counts. This count includes both header and body. And you have next fragmentation. What do you have here? Identification, flags, and fragment offset. So this is about fragmentation. This fragmentation happens, if you recall, there is an encapsulation. All packets are encapsulated into frame. Decapsulation, let's go to images, if you can find any meaningful images. Can you see here, do you have in a very lowest layer, you can see, right, frame there, frames. Can you see here, you have the data is encapsulated, and in a data link layer, that whole data coming from the upper layers is encapsulated, and frame header and frame trailer are added. So here in some networks there is a limitation to this frame size. This is usually the 1500 in some ethernets, and it varies in other networks. So there is a limitation how much this how much body, how much length of the maximum how much data this can IPv4 can carry, which is including the header, 65K, 65,565, because this is this length, this is of 16 size, this 16-bit. If we take a 16-bit number can represent up to 65K, 65,565. So that is a total length. So beyond that, you can't, this IPv4 can't carry. Of course, this can carry up to 65K bytes, but thing is that in some ethernets, the data needs to be fragmented, because this frame size is limited because of some physical the medium limitations, where it varies, it is different in other mediums, and for Ethernet it is 1500. So according to that, we need to do fragmentation. What is fragmentation? Since because of the limitation of the frame of a data link layer, according to the medium, this IP header, IP packet, for suppose let's assume 1500 for the Ethernet, and that is, but this can carry up to 65K. So in such a case, 65K data cannot be encapsulated into this frame, so such that IP packets, IPv4 packets are the packets are divided into chunks, and it is called fragmentation. Each chunk is called a fragment, and to identify each fragment is identified using the unique ID, using identification. It varies for each packet, but for each fragment it would be the same. And flags, there are 3 bits, one reserved and true. One is of do not fragment and fragment. They are used to identify whether it is a fragment or when it is the end of the fragment. Fragment offset describes the where that packet belongs to in a fragmented set of packets. So it is offset of the fragment. And what you have here, time to live, that describes the number of hops. So every time the packet passes through the router or forwarded by the router, this is decremented. Okay, and next we have the protocol. And this protocol, you can see this protocol, it has a numbers. 17 means these are the protocol numbers. 17 means UDP and 6 means transmission control protocol. That protocol is again 8 bits used to represent what kind of protocol this IPv4 is carrying. And next we have is a header checksum. This header checksum calculates the checksum of the header. So the checksum is used to identify uh, the integrity of the header. Are you following along? Or do you have any queries? Okay. Okay. I think we are good. I think I'll continue. Okay. So this let me know if you have any questions as we are discussing. So this time to live is used to describe the number of hops as it is forwarded by the every router. It is documented, but originally uh, it was created when it was designed. It was there to hold the timestamp, but now it is used to hold the number of hops, so such that this packet can't cover. This packet cannot go on and go through the loops and forever traveling without being without going to the destination. And what you have is a protocol and then header checksum. We have the source address and destination address, and then options data we have. So source address is a 32-bit IPv4 address, and the destination address is also 32-bit IPv4 address. And we have the options and the data we have. So this the data is a, as we can see in our OSI model. See, as you can see here in our OSI model, wait a moment. Right. So this seventh layer is encapsulated into presentation, and then that is encapsulated in session, all that is encapsulated in transport, all that is encapsulated in network layer. In that way, this network layer contain, as it is shown in these pictures, all of the data encapsulated here, which is typically the segment and data encapsulated here. Okay, so now let's learn about let's see this thing in action using Wireshark, how this packet is structured. And since this is whole bits that this is how the packet is traveling, but we actually uh, showed this the packet is shown in a pretty manner with the proper fields. Let's see in a Wireshark how that packet is structured, and I can capture that packet on a on a Wi-Fi, but thing is that my network is using IPv6 address, as you can see. So we would be discussing IPv4 uh, such that I downloaded this sample packet. So we can go to help and go to sample captures, and there the IP, search for the IP or a TCP. Search for the IP or UDP or TCP. UDP. Okay. So I took there's a there are these are all sample protocols for different sample captures for different protocols grouped by their protocol category. And then here are the sample captures for the TCP. Okay. So what I'm doing, I'm downloading this TCP. And let's open that in a Wireshark such that we can discuss. Hopefully that contains the IPv4, and we can discuss that IPv4 in action. So Here, let's check. These are all. What do you have here? This is simple capture. It contains only 35 frames, and this is a TCP. How all the data we have here is a TCP, and to quickly check the statistics, to quickly check information about packet, go to the capture file properties, and there we can see the properties of a capture file, or what protocols are involved. Go to statistic and protocol hierarchy, and there you can see the protocol hierarchy. Here the data from the application layer, that is encapsulated into TCP layer, that is encapsulated into the IP layer, and then Ethernet or a data link layer. This is encapsulated. So we have the IPv4 layer protocol, and what you can see here, what different nodes are involved. What is source and destination? You can see the source, destination, source. And if go to statistics and conversations, there we can see the IPv4. We can see only the conversations between 200.135 and 200.21. These are the conversations. These are two nodes involved here. So let's take any of the packet, and we need to see, we should be and discuss how this packet is structured here. Here, as I say, we have discussed the other day, this is a packet list, and we have the packet detail and packet bytes. These are different panels we have. Okay, and different panels we have here, and yes, here is the packet list and packet detail. And this I structured in my Wireshark like this, and you can go to preferences, and there layout, you can choose any of the layout according to your screen size or your convenience. And what for any frame I select here, and I can see those packet details here and packet bytes here. And if you take the frame, this is the frame, all the data captured captured that captured for that packet, you can see here. And I can dump this as hexadecimal format, in hexadecimal format, or in a binary format. Right click and go to dump it as a bits, or dump it as a decimal. And here you can see, and what do you have? Ethernet, which is a frame. It contains the Ethernet source and destination address, which is a MAC. And what you have here is a internet protocol, and it is encapsulates the transmission control protocol. And discussion for the TCP is a should need another session. So we'll discuss and we'll discuss about the transport layer protocols such as a TCP and UDP, and in the next session, comment session. And let's discuss about IPv4. And we have learned about the packet structure. Can you see here the packet structure? The first 4 bytes represent the version. And as you can see here, the first 4 bytes here, I highlighted first 4. Sorry, not first 4 bytes, first 4 bits. You can see here in hexadecimal format, it is representing 4, which means IP version 4. I can toggle this thing as a bits as well. Okay, you can see, right? And as I selected, and the first 4 bits, take the 8421, remember, which is a 4. Okay, next 4 bits are for a header length. And you can see IHL or H length. This is this field is used to count the number of headers. Length of the header in terms of watts. So that we should, which is a 4 byte word, we should multiply that with the 4 to get the actual bytes length of the header. Why we need a field to count the header length? Because the header field size of the header in IPv4 is not fixed. It is varied. It is minimum of 20 bytes or maximum of 60 bytes. And IP header may contain optional 40 bytes of headers or 40 bytes of options or padding. And you have here header length, and that is header length is 20. What do we have here? So it is a 5. As you can see here, convert this first last 4 bits into decimal, which is a 8421, 4 and 1. How much it is? 0101, which means 5. Okay, 5 into 2, 5 into 4, which gives 20. As you can see, 20 bytes. So what do you see here? This whole data is regarding this whole data that Wireshark is presenting for a packet captured in a pretty manner, that we can readable manner, but it is not readable. That computer can only understand what you see in a what you see here in a raw bytes or a packet bytes. Okay, packet bytes, and you have a differential service, which is a differential service is a 0. Okay, differential service which is used, this is, as you can see, a 16 bits type of service, or differentiated service that is used to specify the quality of service data. Okay, so because some real-time data requires so all packets are traveling through the network through the router, and router sometimes need to, so router queues that data and process like a queue those bytes that those packets router is receiving, but sometimes routers need to prioritize. In such a case, router checks this quality of service, and for real-time data such as a SIP, voice over protocols, so this quality of service is used, and uh, service fill is used, and here it is a 0. And we have the total length. As you can see here, total length filler, which is 16 bits and 2 bytes, and that is used to represent the length of a whole packet, including header and body. Here it is 240. So tell me, what is the length of data here? So this here in this packet we are discussing, the length of a header is 20 bytes, and total length of the packet is 40 bytes. In such a case, what is the length of the data? What is the length of? No, so we don't have any options here. That is why we see here 20 bytes. We don't have any options here. So in such a case, total packet length is a 40 bytes and header length is 20 bytes. What is the length of data? 20 bytes. 20 minus 20, right? This is a whole packet, and in this whole packet, header is taking up 20 bytes, and length of whole packet is 40 bytes. And subtract 20 bytes from 40, what you get is the length of the data. Okay, so in IPv4, this total length describes the length of the whole datagram or packet. As you can see here, 40, and as you can see in right side, which is any field I have highlighted here. You can see on right side there, here. And if you convert this to decimal, what you will get a 40, and I can dump it as a hexadecimal, and there you can see 28. And if you want, we can convert that. What is hexadecimal 28? We can convert. So just go to JavaScript console. Here in this console, we can convert hexadecimal to 0x20, which is 40. Okay, so hexadecimal 20 is a 28 is a 40, which is a 40 bytes. And we have identification. As you can see, this identification varies for every packet, unless it is a fragment of a packet. So for all fragments of a signal, any packet would are identified by the same identification value in the identification field. But if they are those packets are not fragments, in such a case, it should be the different for all packets, because that is how receiving end processes, because it captures all packets that have a same identification and consider them as a fragments. And flags we have here do not fragment. 3 flags here. This bit we have, as we can see, we have seen here in this flags there are 3 bits, and 1 bit is for a reserved, and another bit is for don't fragment, and another bit for a fragment, which means more fragments. And here do not fragment is set for a first for a packet which is not fragment, and is also set for a packet which is a last fragment. But here, so this is not a fragment, So do not fragment is set. And what we have here, fragment offset is 0. Why? Because here this is not, since it is not a fragment, so offset doesn't have any meaning, so it is 0. And as you can see here, time to live, which is 24, it is decremented as it is passed through a router, every router. And we have the source protocol, which is 6. As you can see, we have learned just while ago. Yeah, here it is. For TCP, which is a 6, protocol number for UDP 17, for IPv6 encapsulation 41, and so open shortest path OSPF, which is 89, like that. So here, since it is a TCP, that field describes this TCP, the protocol field describes the which protocol this that which protocol, the protocol that is encapsulated into IPv6 packet, just TCP. And header checksum, this is not validated by the Wireshark. And here is it is a checksum which is used to verify the integrity of the header, just in case if it is corrupted when it is passing through, and when it is carried transmitted over the network, and it is verified by the every routers or a destination. And what we have here is the source address and destination address. As I highlighted, you can see here the source address, which is represented in a hexadecimal, so 32 bits, or 8 hexadecimal 8-digit hexadecimal number, okay, or 32-bit binary number. As you can see here, 32 bits are highlighted for source address, and if you go here, destination, another 32 bits are highlighted. And this discussion is this is the discussion for the other day. In a coming session, we'll discuss about detail about TCP protocol and UDP protocol, transport layer protocol. This is how the powerful the Wireshark is. You can capture, and also you can use the data that is presented by the Wireshark to debug, troubleshoot, but also more than anything to learn about the protocols, to dig deep into protocols. So when you are working with the network layer, so you are the administrator or network engineer, when you are working with the network level stuff, in such a case, protocol, the Wireshark is your friend. And you can see this, whatever we have discussed, this header format, that is presented in pretty manner here by the Wireshark in a verbose manner. And that we can see here, if you go and highlight the internet protocol layer, you can see that all bits that are highlighted here on right side in a packet bytes panel are related to the header of the IPv4. Thank you. I hope you understand this IPv4 very well. Packet structure, in fact, that is the structure or format of the IPv4 header in detail using a Wireshark. And in the coming session, we will explore different protocols, and we will see the fragmentation, we will see routing and different protocols. So the Wireshark, and go and explore the sample captures here.